In this lesson, we'll focus on how do cells get energy. Now, in a previous lesson, we described the cell membrane and what it's made of and what are some of its important tasks. It's going to regulate, control the flow of material into and out of the cell. Food, for example, has to come into the cell. In this lesson, we'll take a look at what happens to that food. The food is going to be a source of energy and building materials. We'll focus on the energy first. First of all, we need to identify where all this is happening. The chemistry of life is going to be happening in the cytoplasm of the cell, and that's a thick fluid, mostly water, but with lots of other molecules dissolved in the water, proteins and many other types of molecules. And this is where the chemistry of life occurs. So what exactly is the chemistry of life? Well, a lot of it has to do with getting energy from food. Now, you have an idea of what food is to you, but for a cell, this thing right here is a delicious meal. So glucose is a molecule composed of atoms. So we got carbon atoms and oxygen atoms and hydrogen atoms. This is an ideal food molecule for a cell. All molecules store energy in their chemical bonds, so breaking bonds releases energy. Thus, food molecules can be a source of energy to power cell activities. Cells release the stored energy in food molecules to power the construction of the cell's own molecules. So, the chemistry of life then, a lot of it has to do with processing energy, extracting energy from the environment, taking useful molecules into the cell and then working them over. And a team of proteins is required to extract the energy from food molecules. So how is it, though, that food molecules actually store energy? Well, first, we're going to have to revisit the concept of energy. Now, physicists define energy as the ability to do work. And we'll make a distinction between two kinds of energy: kinetic energy, the energy of motion, and potential energy, the energy of position. And we can see the two kinds of energy in these two diagrams here. So potential energy can be transformed into the energy of motion. Imagine using a pulley to pull this weight. It was right here, and you pull the cord over here, and then the weight goes up to this position. We have just increased its potential energy, the energy of position. We've done so because we live on a planet with gravity, and it took work. I had to pull hard on this cord to move that weight to a higher position. So I've increased the potential energy of this object. If we were to cut the cord, that potential energy is being converted into kinetic energy as the object accelerates towards the ground. So this is the force of gravity causing that acceleration. But we can think of it in terms of energy. I increased the potential energy of the object, the energy of position. I had to do work against the force of gravity. And now when I cut the cord, the force of gravity accelerates the object, so potential energy is being converted into kinetic energy, the energy of motion. Of course, then it hits the ground. Same thing for a swing set here. So as the kid is swinging, so when they reach the highest point in the swing, that's the highest potential energy, the highest distance above the ground. It takes work to move the person up higher above the ground because you're always acting against that force of gravity. As the kid starts to swing down, then some of that potential energy is being converted into kinetic energy, the energy of motion. The kid is moving in this direction. And the amount of energy converted is just the difference in height here. So he's at this height, now he's at this height. Well, that difference in height is a difference in potential energy, and that's going to be converted into the energy of motion. And that energy of motion is going to be converted into potential energy again. So that energy is going to move the child higher up to some highest point, and we're increasing the potential energy again. So the swing then is an example of how potential energy can be converted into kinetic energy, and kinetic energy back into potential energy. In the case of a dam, for example, it would take work to move a bucket of water, climb up this hill and get onto the bridge. It would take a lot of work to do that. I have to expend a lot of energy, but I'm increasing the potential energy of the water if it is at a higher level than it was before. So the way a dam works is that the barrier here, the dam itself, is going to back up this water. And then what they're going to do is allow that water to fall down So to a lower level here, so we've got potential energy. The water is stored at a higher position. We're going to let that water fall, and that potential energy then is converted into kinetic energy, and that falling water is going to turn a turbine, which is basically a coil of wire in a magnetic field. And when you turn a coil of wire in a magnetic field, you generate electricity. So you're converting potential energy of the water at a higher position here. As the water falls, that potential energy converts into kinetic energy, and that can then be used to do work on a turbine, to turn the turbine, and that generates electricity. Now let's get back to molecules. How do molecules store energy in a chemical bond? The answer will be chemical bonds store energy because it took energy to make the chemical bond. Let's see why. Here we have a hydrogen atom here. We have a proton and the electron. Here we have an oxygen atom. We've got 1, 2, 3, 4, 5, 6, 7, 8 protons, and we do have the neutron shown here. We've got 8 electrons. And we know that if the oxygen atom makes 2 chemical bonds with hydrogen, then we have a water molecule. But let's take a look at how that chemical bond has to be made. To get the oxygen and the hydrogen to bond, we have to move that hydrogen atom closer and closer and closer to the oxygen atom. But notice, as you move the atom closer, the electrons in the hydrogen and the electrons in the outer shell of the oxygen are going to repel each other. They're both electrically or negatively charged. So that's going to be a repulsive force. So we're going to have to do work to get the atoms close enough together to make that chemical bond. If we have enough energy to push them close enough, then what can happen is that the oxygen nucleus, the positive charges here, start to attract the negatively charged electron from the hydrogen atom, and the hydrogen nucleus, that positive charge, starts to attract one of the electrons of the oxygen, and that's the position where we can now make a chemical bond. So the oxygen and the hydrogen are going to be sharing this pair of electrons. So basically, when the electron orbitals overlap, the electrons can be attracted by both nuclei. Each electron of the pair will orbit both nuclei, and that's a chemical bond. But remember, we had to do work to get those two atoms close enough to bond. And if we have to do work, it means the bond itself is going to be storing energy. So the energy used to bring the atoms close together is now stored in the chemical bond. So the bond has potential energy. So, chemical bonds store energy, the energy it took to make the chemical bond, in a sense. So it takes energy to make a chemical bond. As a result, molecules store potential energy in their chemical bonds. This means then, if we were to break these chemical bonds, we can release that energy. So specialized proteins uniquely suited for this task begin a chemical breakdown of the food molecule. So when we think of food molecules, you want to think of a bundle of potential energy stored in the chemical bonds, and if proteins can begin to break apart those chemical bonds, the cell, in a sense, is getting access to energy. So the chemical bond is broken, so this protein here is going to take a bite, in a sense, out of that molecule, break a chemical bond, and this is the energy, the valuable energy that the cell is trying to harness. And we call all of these chemical reactions metabolism. It's the set of chemical reactions that keep the cell alive. These reactions are performed by proteins, and some of the reactions involve harnessing energy from food molecules. And this energy, of course, is going to be used to power the chemistry of life. Now, to see the value of these proteins in doing the chemistry here involved in getting energy out of food, we're going to use a little graph like this. And we're going to show energy on the y-axis and then the reaction kind of time proceeding on the x-axis. And let's think about getting the energy of glucose by burning it. Instead of proteins breaking apart, we're just going to add a flame. Now, the flame is a large input of energy. But the flame will do a job. It'll break these chemical bonds, and we can extract all the energy stored in glucose by using a flame. And that's shown here. We've got the reactant would be glucose, and we're going to add flame, but it takes a large input of energy to break all these chemical bonds. The result of that burning will be carbon dioxide and water, and those molecules have relatively less energy. So all the energy produced by burning that sugar can be dissipated as heat. But the point is that a flame is a large input of energy that is needed then to break these chemical bonds. But it can be done. And the result is low energy molecules, the waste products, carbon dioxide and water, and then heat. The heat of the burning is released to the environment. Now notice what a protein does. What proteins do is they reduce the amount of energy you need to start breaking these chemical bonds. So we don't need as much energy as a flame. The protein makes it so that you can start breaking these bonds with less input of energy. So we lower the activation energy. And again, you get the same products. You're still going to be ripping apart this glucose molecule into carbon dioxide and water. And we get the same amount of energy released from that process, but it just took less energy to get the process started. That's the value of proteins. In reality, inside a cell, it's a team of proteins that are doing one step in a long chain of chemical reactions. So several steps are required. But in the end, the same amount of energy is released from the food molecule as if it was burned. So you can take a flame and burn sugar and get your waste products and then some released energy, or you can step by step have a team of proteins breaking each of these chemical bonds. You'll still release the same amount of energy, but you won't need as much energy in the beginning to get the process started. So let's put it all together now and see what cells are doing when they import food. Food is a source of energy and building materials. The cell is going to break apart the food molecules to retrieve that energy stored in the chemical bonds of the food molecules. In addition, some of the food molecules can be used as building materials. Now, when you do the chemistry, when you extract the energy from food, some amount of heat is released to the environment. And this is why all living things generate heat. Now the cell's going to use the extracted energy, it's going to harness that energy and use that energy to do further chemistry. Using the nutrients from the food, the nutrients will be the raw materials to build important molecules that the cell needs to construct. Perhaps it's going to make some DNA or make some proteins, or it's going to build new lipids for the membrane. Well, that takes energy that was originally stored in the chemical bonds of food, and it takes raw materials, again imported as food. So this is what we mean by metabolism. This is almost half of metabolism is extracting the energy from food and getting the raw materials ready to do construction projects. That's the other half of metabolism, doing the building process. So we've got cells extracting energy from their environment and using that energy to build important molecules in the cell. So what we have here now, we're starting to add on to the process. We have the cell membrane is going to regulate the flow of food into the cell, and then the cell's going to use those food molecules, break them down to extract energy. In addition, some of the food can be used as building material as well.